Yeah, thank you for the introduction. Yeah, actually, I slightly changed my title here because I want to include a very recent work on the MOT setting. So the new title here is on the 3D object tracking in point clouds and best practice and new settings. I'm Naiyan. It's my great pleasure to present our work here in this workshop. Okay, so before going to the details of work, let me briefly introduce a different paradigm of tracking. Briefly speaking, there are two types of object tracking. The first is the so-called multi-object tracking. In the multi-object tracking setting, it's mainly focused on the association of bounding boxes across different frames. It relies on a detector to output the bounding box of interest first, and then to associate those bounding boxes across different frames. The drawback of this MOT setting is that it heavily relies on the performance of detection. And on the contrary, there's another type of object tracking is called the single object tracking. In the single object tracking, we don't assume the detection the detection is given in each frame. So it only need an initial bounding box in the first frame and subsequent point clouds. So briefly speaking, the 3D SOT can be divided into two approaches. The first is a discriminative approaches. The representative work is a P2B, and the generative work I will introduce later. So the first work I want to introduce is we have a ablation on the 3D MOT pipeline. We first modulized the current 3D MOT system into 4 components and study the details of each one. And we found some very simple but very effective best practice in current system, and it could improve on many data sets significantly. So briefly speaking, we divide current 3D MOT system into 4 components: the detection preprocessing, association, motion model, and lifecycle management. For the preprocessing part, we need to pre-process the input detections using some techniques like AMS or store filtering to keep some detections. We'll get into the subsequent pipeline. We need to filter out some low quality detections or the redundant detections in this step. But we found that in this step, there are many details can be improved the performance. And the second part is the association. In the association part, we consider of 2 things. The first is the similarity matrix. It computes the similarity between objects, and also the matching strategy. It defines how we assign detections to each tracklet. And the third one is the motion model. In the motion model, we model the movement of objects and predict next state. The last one is the lifecycle management. And actually, this is almost nobody mentioned this part in MOT paper, but it's from our experience, it's a very important component to maintain a good tracker system. It controls the initialization, the output or not, or the termination of a tracklet. Currently, this part is very heuristic. There's no principal way to improve this management. So we think there are a lot of work can do in all these 4 components. So we summarize some best practice and test them on the Waymo and NewSense dataset, and we hope that we could our method could serve as strong and simple baseline for the 3D MOT. And beyond to provide the best practice, we also rethink current benchmark. And we found some settings are not that reasonable in current benchmark. The first is the AMOTA metric used in NewSense can be easily hacked. I will cover these details in later slides. And the second is the 2 Hz setting. The low FPS setting in NewSense actually brings unnecessary difficulties. So if we use a higher FPS, actually the performance also can be easily improved. So also will be covered in later slides. Okay, so I'll go into the details of the best practice. Okay. Before going to the details, there's also very quick review of recent 3D MOT method. It can be seen that almost all these methods can be casted into our pipeline. For example, center point is actually use neural network to improve the motion model to predict the velocity, and CBMOT is to refine for the lifecycle management, and PNet is using deep learning based graph matching for association. So we think that the modulizes, if we can modulize the 3D MOT system into different components, we can better understand which part is the most important and how they affect the final performance. Okay, for the first part is the data preprocessor. We found that in current practice, we don't perform further NMS on the raw detections. I think maybe the reason here is to fit the AMOTA metric to provide the results at high recall. But we found that these noisy and inaccurate detections actually will be harmful for the final performance. If we simply apply NMS on the raw detections, both the AMOTA and MOTA will increase about 1 point, and the eddy switch will decrease. So the intuition behind this idea is that the object, in contrast to in the 2D space, the object cannot overlap in the 3D spaces. So we only need to keep the most accurate ones in 3D space. But if we keep many inaccurate bounding boxes, they will affect the association step in the next. We may associate a tracklet with a detection that is not of high quality, and it will affect the final AMOTA and MOTA performance. So the takeaway here is if multiple hypotheses in the tracking should be handled, but if we cannot handle it, simply keep the best. It will bring the best results. And the second is on the association metric. We find that the LU-based method truncate in zero. That means if two bounding boxes they don't overlap, so the the traditional LU will not be discriminating in this case. But on the contrary, if we use a distance-based method, it's very prone to drift because we cannot consider the actual overlap of two bounding boxes. So we asked whether we can have a better method. So fortunately, we found that there's a work is called the generalized IOU. So the basic idea is to combining these two aspects. So it finds the smallest encoding convex object and using this convex object to adjust the IOU, especially when two bounding boxes they don't overlap. But in this case, the GLU will be more discriminative in this case. So apply simply replacing the LU to TLU, we found that in both Vim Open Dataset and NewSense, we could improve the ID switch significantly. For example, if we use GLU on the in the Vim Open Dataset, we can find the ID switch can drop from 0.13 to 0.07 is almost a half, reduced by a half. And also for the NewSense, the results are even more significant. The reason here is that NewSense uses a 2 Hz setting is more sensitive to the bounding boxes that they don't overlap. So in NewSense, we could improve upon the IOU by about 6 points, just replacing the association metric and reducing the 2/3 of the ID switch. So the takeaway in the association part is the similarity metric should be discriminative all the time. Okay.
Hi, Naiyan.
Hey.
Yeah, can I just interrupt here for like 1 minute? Because this is like a really quick clarification question for the previous slide. So the association matrix. So here you're talking about the GIU is doing really much better than the standard IOU, but where do you talk about? So here, when we do the 3D model tracking, there are two places where we are using the IOU. The one is using the data association for tracking, basically in your model, right, to produce a result. And the other one is using in the evaluation. So you want to match your tracking result with the ground truth to compute the number, right? So that's also need to have some metric. Let's say GLU. So where are you talking about? It's in the evaluation or it's in your model?
Only in your model. Yeah, to replace the
So the evaluation, for example, for new things, you are still using the distance.
Yeah, exactly the same evaluation metric.
I see. Okay, that's really good to know. Thanks.
All right. Okay. The third part is lifecycle management. So the basic idea is also very simple. So we want to use the boxes with low score to keep the life cycles. For example, in the first row here, if we don't use if we prune all the low score detections, then it will contribute to an ID switch. But if we use the low score detections to associate between each frames, but we don't output such low score detections, it will not contribute to the false positive in multi-metric, but it could associate two tracklets into one and reduce the eddy switch. We also try to use the low score detection to update the motion model in the MA2 system, but we don't find this helps a lot. But the association itself, it could reduce the eddy switch by a half. So this is we think it's a very important finding here. So the takeaway here is that actually the detection with low score indicates the existence of objects. So we could use such dark knowledge exists in the detection output, but we simply throw them out in the traditional approaches because we think that they're not accurate enough for tracking. But it actually indicates the existence of an object can be used to reduce the eddy switch. Okay, so these are the three best practices we found in the current system. And the second thing I want to mention is that for the evaluation metric, AMOTA is indeed well motivated and carefully designed. But we find one issue is that we force to output the low score detection to keep record. So we can easily hack that. We can use the motion model predicted box output for those low detection score, that low score detections. But we set the score for such predicted box with a minimum score, such as 0.001, and its score is lower than all the detected bounding boxes. But we find that if we're using this method, we can improve the AMOTA by about 2 points. So, but we don't think such approach is meaningful in real-time application because you don't want to so many false positive in that case. But it indeed improved the AMOTA because you need to output the low score detections to keep that record. And the second finding is that on new things data set, the evaluation is performed on 2 Hz, but currently modern LiDAR and 3D detectors are commonly operated faster than 10 Hz. Actually, we have better motion and the association information when using high FPS detections. So we also try to include the high score boxes in 10 Hz because if we're using the bounding box with too low score, it will make the evaluation on keyframes, the 2 Hz keyframes drop. But setting a threshold such as 0.5 and combining this with the 10 Hz detection, we can also improve the MOTA by 1 point and AMOTA by 1 point. I think this is also a unrealistic setting for current benchmark. It can be improved to more modern settings or even more. For example, on the onboard system, it's at least run as 10 Hz, and I know that in many companies their system running maybe at 20 Hz. So this causes a lot of difficulties that does not exist in real-time practice. Yeah, so we combine all this together, and on the new scene data set, we use the center point detections, and combining all these techniques, we could improve the A motor and motor by about 3 points and reduce about 1/4 of the eddy switches by using all these simple tricks. Yeah, and for the Waymo open dataset, the trends are also similar. And for the pedestrian, it's even more significantly improved on the AB3D MOT. The motor could improve about 7 points. That is very, very significant. And 3 points on the motor and half on the eddy switch. So that's all for my first part. So we study some best practice for the current 3D MOT system. Hope this could help. Yeah. The second work I want to introduce is on the 3D single object tracking. It's accepted by IROS, and the paper has already uploaded to archive. Yeah. So the problem definition for the 3D single object tracking is to give a sequence of point clouds and one initial bounding box. We want to estimate the pose of the same object in the subsequent frames. Different from the MOT setting, in the SOT setting, we don't care about the association between frames because there's no detections given in subsequent frames, only the raw point clouds. So we need to find the bounding boxes by the algorithm itself. So why we need why we need SOT if we already have MOT? So there are several reasons for that. For the online part, the SOT could serve as a backup for the MOT system because the MOT system is sensitive to the missing detections and incorrect detections. But in certain cases, we want the precision of the tracking system to close to 1 because that is very important in the closed area. If we miss one target, then we will cause a great danger for the crash. And for the offline part, there are also many applications. For example, the motion ground truth generation, we could use the SOT algorithm to generate the ground truth velocity and the location of object of interest. We can also use the aggregated shape for the LiDAR simulation, and for the optical flow annotation, use the Kitty dataset. Here is a demonstration video for the use of SOT. So here is along the tracking process, we aggregate the point clouds. So you can see that as the tracking goes on, we can almost get a very dense shape along the tracking. There's more examples for the aggregated shape. And by using the aggregated shape, we could simulate the LiDAR scans. Yep, this is the LiDAR simulation scan. So we first using the SOT to aggregate the point clouds for one object. And after we get this aggregation results, so we could simulate the scan pattern of LiDAR and to get this simulated object. It can be used for the validation of the detection system. Yeah. So serve this goal, we first built a new benchmark. It's called LiDAR-SOT, based on the Waymo open dataset. On Waymo open dataset, there's a large amount of data. It's 9.9 million 3D bounding boxes. So because we're concerned about the tracking, the single object tracking setting, so we filter out all the tracklists less than 100 frames and only keep them the frame numbers larger than 100. And you can see on the right side, most of the tracklist has 200 frames. That's the longest frame numbers for the Waymo open data clip. And we also limit the initial number of points. We eliminate all the tracklists that the initial time frames has less than 20 points, because for the SOT setting, the initialization is very important. If there's almost no observation in the first given bounding box, then it will not create a meaningful tracking results. And the third one is that we remove the tracklist, the vehicle stays all static at the time, because we found that in Waymo dataset, most of the vehicles are stay static. So this will create a trivial solution. You just output the vehicles stay at the same at the first frame. Then this will also get a reasonable good result. So we don't want this happen. So we exclude all the tracklets that the vehicle stays all the time. But we include the sequence that the vehicle stays static at the first, or then it starts to move, or it moves at first, and at last it stays static. We keep such sequences for evaluation and training. Yeah. For the evaluation metric, we have two parts of evaluation. The first is for the state estimation. We follow the settings in the 2D SOT setting. We define the two metrics is the accuracy and robustness. They are orthogonal in some sense that they evaluate different property of the tracker according to their claim. Yeah. So the first metric is the accuracy. It's simply the mean IOU along the sequence. This is very this is a very simple one. The second is called the robustness. Robustness actually calculates the first failure point and a different LU threshold. We want the tracker to track the objects above an LU threshold as long as possible. That's our goal. So we set different thresholds for the evaluation, and we find the first point, the first frame that it falls, the LU falls under that threshold, and this serves another metric for the state estimation. And we also concerned about the shape completion. We want to evaluate the quality of aggregate shape. So we use the chamfer distance between the aggregate ground truth and the aggregate shape, which downsample to 5 centimeter accuracy, and use the chamfer distance between these 2 point clouds as a metric. Yeah, so this is a benchmark and data set we proposed in this paper. For the method we adopt in this it's a very simple baseline. So for the technical part, it's very simple. It's an optimization-based method to optimize the states we are interested given the inputs. So it consists of four terms. The first two is the ICP loss between 2 successive frames and the aggregated shape and the current frames. This serves as a registration between the point clouds. And we also include the motion consistency and motion prior. It serves as a prior for the vehicles moving on road, because we know that the vehicles on road is not a point. It cannot change its heading. It cannot change its heading all the time. So for the motion consistency, we regulate the direction of the velocity to be aligned with its heading. And for the motion prior, it's just a moving average of the previous motion. Definitely, we can use better motion models such as a common filter and something like that. And we also have some details in the baseline method. We find that the ground removal is very important because the ground points will contribute a lot in the SCP loss if we don't remove it. And due to the sparsity of point cloud, we can overlay the LIDAR points in nearby frames and use this for the SCP loss. And we also find that we need outlier rejection to suppress the noise caused by the changing of view because the vehicles are moving. In one frame, we can observe certain part of the object, but in next frame, maybe we cannot we cannot find them. So this will cause an SCP drift. So we use all these 3 techniques to improve the baseline. So here's the results. Because there's no other method, this is the first benchmark proposed, so there's no other method could be compared. First, we can see that all these components contribute to the final performance. And for the ICP baseline, we can improve them significantly on that. And we also try the model-based setting is that we have the detection output in each frame each frame, and we add another detection loss to regulate the output of the SOT tracker to be close of the high score detections in the subsequent frames. And we find that even in this setting, the SOT can also improve the pure detection results. So that's proved the usefulness of the SOT. This is for the first work for the SOT in point clouds. Basically, we propose a benchmark and its associated metrics, and we provide a very simple baseline for the evaluation and justify each of the design choice. Okay, the last term is also for the SOT setting. It's called the online adaptation for implicit object tracking and shape reconstruction in the wild. So the basic idea of the last work is that by tracking the object over time, we can reconstruct better and better shape close to the ground truth. And also that these ground truths, this shape prior in turns could help the tracking, especially when the point clouds are sparse. So we need a model. We need a very good prior and model to regularize this motion. So we can do the shape reconstruction and the tracking at the same time. We want to integrate these two tasks into one single method. So method we use is it's called DeepSDF. It's actually a neural implicit function used for the standard distance function. So the basic idea is also very simple. The SDF actually defines the distance. Given a point is distance to the closest surface. So the DeepSDF is to use a neural network to approximate such function. So so the DeepSDF is a coordinate-based MLP, and that to given a coordinates in 3D space and output the distance to the surface. So the training goal of the DeepSDF is to minimize the distance of to minimize the surface, the distance of the surface and the implicit function. So the method is quite straightforward. So we could use the initial object pose provided in first frame to initialize the shape. We fine-tune the pre-trained the DeepSDF model with the provided initial shape in the first frame, and in the following frames we iterate between the registration between the shape and point clouds and the fine-tuning the shape code of SDF. So our goal is to jointly estimate the pose and the adapted shape. So in the subsequent frames, we first use the aggregated SDF function to find the tracking results. So we first estimate pose with the previous shape and SDF. So we estimate pose by pushing the point clouds to the 0 level set to the SDF field. By using this method, we actually register the point clouds to the implicit SDF function. And after that, we use a aligned point cloud to improve the shape quality. So in the shape adaptation part, we use we deform the SDF field to match the cloud. We fine-tune the SDF code using the aligned point clouds, and by iterate between these two steps, we could get a reconstructed shape at the end of tracking, and along the tracking use the improved shape to help the drifting problem in tracking. Yeah, this is a very simple, effective pipeline for the online SOT tracking. Here's a demo of the shape evolution and the tracking results. As you can see that the shape gets more and more to its ground truth along the tracking. Another example is for a large SUV, but the mean shape at first frame is only a passenger car. we could improve the shape reconstruction along the tracking. Yeah, this is the visual result. And we experiment on both Waymo and KD dataset and compare with SOT tracker and other discriminative trackers such as P2B, and we found that our method, yeah, is quite effective. Especially on the hard case, it improved the accuracy and robustness by about about 5 points in robustness and about 8 points in accuracy. The difference between the SOT tracker and the one with shape reconstruction is not that significant in the easy split, and even on the robustness evaluation metric, the easy part is the SOT tracker gets better results. And for the shape reconstruction, the trends are similar. We're still better than the P2B SC3D in terms of chamfer distance and recall. And an interesting ablation is that interesting ablation is that whether the shape improves along the tracking process. So we compare the reconstruction quality by using different depth frames. As we can see that if we use about 40 frames, the performance just saturate. So if we can use more frames, the performance we think that could still improve. Yes. So the tracking and reconstruction performance continue to improve as the number of adaptation frames increases. So that's almost all for my today's talk. So the takeaway message is the 3D multi-orbit tracking needs careful treatment. The devil is in the details. By only combining simple techniques, we have surpassed the all-SOTA method on the two popular benchmarks. And the second one is the 3D single object tracking is also valuable. So the new dataset and benchmark are provided. We hope that we can have more method to be evaluated on this new benchmark and using this new metrics. And joint modeling of the related tasks such as the shape reconstruction help both tasks. And we could explore more related tasks from downstream applications to improve the tracking and also improve the downstream applications. So the future work, there are two I think that's worth studying. The first is how to incorporate the multimodal input for SOT. Apparently, we don't use image for SOT, but definitely I think it should help in this case. And the second is how to handle the non-rigid objects in SOT, such as a pedestrian. We don't have the rigid assumption for the objects, so we may need some deformable methods for the tracking of non-rigid objects. Okay, that's all for my today's talk. Any questions?
Thank you, Naiyan, for the very good insights into these metrics. I think there's one question in the chat.
Yeah, I have a query regarding the car shape shown on the right side in previous slides. So is that a mesh? If yes, then what is the procedure for moving from SDF to mesh? You mean in this video? Assuming this video?
Yes.
Yeah. Yes, using the melting cube to the mesh. Yeah, we convert the SDF to a mesh. There's a previous work can do this job.
Can you please mention that work so that I'll just read that?
Yeah, I think the traditional melting cube could help.
Okay, thanks.
I have a general question.
Mm-hmm.
It's like just I come from like classical tracking community, and just like one of the things like when reading like recent papers on tracking is like they are completely ignoring like classical tracking approaches. Just like for example, like on this slide, you're essentially like accumulating like points over time just to increase the SNR to get the better detection. And so yeah, like is it true?
Sorry, I cannot hear that clearly. So could you repeat your question? Yeah.
Like you're accumulating points to get like better SNR, like signal to noise ratio, and like to get better detection in the end. Like in this case, for example.
Yeah.
But like this is like track before detect, and it's like 20 years old.
Oh, sorry, my network is a bit bad. Can you type your question in the chat so maybe you can better hear your question?
Like you can you hear me?
Yeah, it's okay for now, but when you speak, that is not that good. Yeah, can you type your question in the chat so maybe I can understand your question better?
Yeah, I guess while he's typing, I also have another question. By the way, Naiyan, can you hear me clearly?
Yeah.
If not, I can also type, but
yeah.
Okay, so let me just try. Yeah, let me just try to ask. So first of all, like I really like to hear this talk. Like you said in the email, this will be a very interesting topic to me because I have been working on the MOT, especially in the first half you are talking about. So I want to discuss with you about a little bit the follow-up discussion on the metric, the MOT on the new things. So when you say that it can be easily hacked by adding more boxes to kind of maintain the recall, right? So I think you're right because the MOT metric is designed to favor more for high recall method because you're computing the area under the curve, right? So basically, if your curve has a higher recall, that means you have a more area to compute the area under the curve, right? Because you have a higher X. Yeah. Like so in that sense, so in that sense, it's kind of making sense. You're getting higher MOT because you're increasing the recall. But in other sense, I don't think it's completely useless in the real world because you are not just adding garbage boxes, right? You're still adding some boxes because otherwise you won't increase the recall, right? Since you have increased the recall, that means some of the boxes you add are correct. Or so that sense, in that sense, so in that sense, it's still good to have those boxes in the real world, right? Because you don't want to have a low recall, and that's really like safety critical problems.
Yeah, the key here is that just like in detection, we all use MAP for the evaluation in academia, but actually we don't use MAP on board testing. Why? Well, that we use metrics such as FPPI for the evaluation of detections because we need to set a threshold for detections to downstream applications. So that's the difference here. I think the AMOTA is very similar to MAP. It wants to calculate all the curves, but actually even the MAP is not that meaningful in practice. From my side,
I guess at the end, this will be not the metric you will use to measure the system. It's just a tool to analyze your system. Like how is your precision and recall correlate with that? So it's just an analyze tool rather than a silo score to rank your system, I think. In that sense, I just want to say in that sense, you are totally correct about this.
We think that we may need another metric to indicate the performance if we have a threshold on the detection on the tracklist score detection score.
I guess that in terms of the mass metric, I have been working recently like with my advisor and also industry collaborators. So we are more kind of lean towards to use even more downstream to evaluate tracking. So not just using tracking metrics to evaluate tracking, but more, let's say, using planning. Basically, if you only have the tracking metrics, the score for the tracker, it's not enough the world, right? You still have to run prediction, you have to run planning. So you have to know the final performance of your system So for example, if you change the tracker to something else, what's the fellow planning performance will change, and then you will use that to measure the tracking performance. So it's like a planning aware tracking evaluation. So because that's probably the end of the ultimate thing we will need to do. But right now, AMOT is really an intermediate thing that we have. But I don't know. I mean, we can probably improve AMOT as well before we reach that point. If you have some just suggestions, I would be really glad to hear.
Yeah, we can have emails discuss on this metric. Yeah.
Yeah, definitely.
Yeah. The question is that I find a lot of recent tracking papers are kind of ignoring classical approaches, accumulating points over time to increase SNR for better performance. Have been extensive study in tracking before detect approaches. Death and birth heuristics are also studied in Gaussian mixture-based and MCMC filters. We think we are aware of some work, and actually myself is working on 2D tracking, and especially the particle filter based tracking in my PhD study. Yes, but the key is here we find that for the MOT setting, they don't care a lot about the life cycle management here, and so we want to mention the researchers in this area. This is very important for your performance. You have to make it correct. Yeah. And Gaussian mixer model and MCMC filter. Yeah. The MHT and GPDA are classical approaches for that. Yeah, definitely. And maybe the problem of MHT and GPDA is the computational cost for that. Yeah, if we keep a large set of hypotheses, the tracking speed of these approaches will not be acceptable. Definitely, there are many improvements on MHT and GPDA.